All right, wonderful. So we're delighted again and really appreciative of Duff Neill taking the time to talk to us for the second week. Duff received his Ph.D. from Carnegie Mellon in 2012, was then a Pappalardo Postdoctoral Fellow at MIT through 2016, and then went to Los Alamos National Laboratory as a Feynman Fellow, where he became a permanent staff in 2020. That's just a brief review of what we said last week. And this week, we're going to learn about soft collinear effective field theory from one of the world experts. So we're really, really thankful to have this opportunity. So Duff, when you're ready, please take it away.
All right, so this is mainly a brief recap of what I talked about last week. In order to formulate an effective theory, we need these set of ingredients. What are the degrees of freedom? What are the symmetries of the problem? What are the power counting? And then at the last bit, we'll need some sort of principle of least action / path integral. And I'm going to talk not very much about that last point because that's, something that should be covered in QFT1. And the main point is that if we don't have all of these ingredients, then we will be unable to formulate an effective theory. So in this talk, I'll be specifically focused on what are the degrees of freedom we need and symmetries, and what is the power counting when we're thinking about high energy scattering processes in quantum chromodynamics. So in my construction of SCET, I'm going to loosely follow this particular paper that I wrote, I guess, a decade ago now. It doesn't feel like it was a decade, with some colleagues at MIT. While we didn't set about constructing SCET, we had hoped to engineer that paper to be a broader audience than the SCET community. So it does contain a fairly complete discussion of how you would go about constructing SCET, complete, but also in the fastest way possible. But also what's good about that paper is that it has a fairly complete bibliography of the foundational papers of SCET and a lot of the applications of SCET up until 2014. Since then, a lot has happened, and well, not going to get into that just yet. So what are we thinking about? In particular, we're thinking about the theory of strong interactions, which consists of partons. And by partons, I just mean that there's going to be gluons, which are the spin 1 force-carrying particles of the theory that transform in the adjoint of your gauge group. And then there's going to be quarks, which are spin 1 half matter that transform in the fundamental. And the interactions between these two, quarks and gluons, when your gauge group is SU3, form quantum chromodynamics and is responsible for all of basically nuclear physics at some fundamental level. But in particular, it's responsible for how protons and neutrons are bound up together, how gluons and quarks form protons and neutrons, and then how those things can bind up together to form nuclei. SCET is a particular effective theory of QCD that describes the long range and low energy dynamics of high energy QCD scattering processes. And so what you'll run into when you're going to calculate a high energy scattering process typically is that there's going to be very many scales in your problem. One is going to be whatever's the hard interaction scale where your scattering process takes place. But we also just know that there will always be at least one other scale in our problem whenever we're talking about QCD, and that will be whatever's the scale of confinement. And so you can think of that as being approximately the pion mass. And so if I'm talking about high energy scattering at the LHC, then I'll have hard interactions of orders 100 GeV, but the pion mass is lowly at 100 MeV. And so there's going to be very many decades of energy scales between those two. And we would need to be able to describe the dynamics across all of those decades of energy scales in order to give an appropriate description of the QCD scattering process. And this is what SCET has been formulated to do. Now, as a particularly clean example of a high-energy scattering process in quantum chromodynamics, I'm giving you the detector readout of the Opal detector, which was a detector at the precursor to the Large Hadron Collider, which was the Large Electron Positron Collider at CERN. And the Large Electron Positron Collider at CERN was tuned to these, well, it was tuned to multiple different energies, but one of the most famous energies that it was tuned at was the center of mass energy at the Z-pole, 91 GeV, so that when they collided their electrons and positrons together, they made a plethora of Z particles, and those Z particles liked to decay to jets, mainly because the strong coupling constant is fairly large, and so you get a pretty large enhancement for any decay to jets. The blue lines in this picture, you shouldn't actually, I mean, you should think of those as being the tracks in your detector. So generally detectors have two different systems. One is going to be a system which just measures the amount of energy that's deposited in a particular cell. And then the other one is going to be the tracking system, which measures basically how a charged particle gets bent by a magnetic field as it travels through your detector. And by combining the information of these calorimeters and these tracks, they're able to reconstruct basically all of the momenta of the final state particles. Now, we can already talk about the separation of scales in this particular picture. That little star point is supposed to be the hard interaction point, which is at 91 GeV. However, all of the particles that are impinging upon this detector, they're going to be at roughly the scale of hadronization. So at best, you're looking at particles that have a 1 GeV mass because there's going to be a couple of protons and neutrons mixed into that. But by and large, most of those particles were kaons and pions in any given scattering reaction. And so what we would like to be able to do is describe how we went from an electron-positron colliding together, the formation of this Z boson, then its subsequent decay into quarks and gluons, and then those quarks and gluons' subsequent hadronization into pions, kaons, protons, and neutrons that are then what's wind up in our detector. And once again, we're going to sweep through many decades of energy scales to do this, 91 GeV all the way down to lambda QCD. And we would want to be able to give a reason why we see the particular pattern of radiation that we do. So most of the events that happened at the collaboration looked exactly like the one that I'm showing you right here. You had a spray of particles impinging on one side of the detector, another spray of particles impinging on the other side of the detector. And we would like to be able to characterize those sprays of particles and sort of explain why that is the predominant features that we saw. We would even want to do one better and say predict the cross-section for each of these sprays as, say, a function of the width of that spray. And there's various different measures that people wrote down for the width of that spray. And in general, that spray would be called a jet. And in fact, if you were able to zoom in on this particular slide, you can see that they quote some of the measures of the width of these sprays. The thrust, the aplanarity, the sphericity, and the oblateness all give you certain different characteristics of the width and geometrical shape of the final state. And you would like to be able to state for the experimentalist what was the cross-section that you should have expected to see for that particular value of each one of those parameters. The easiest one to explain, of course, is just the thrust. The thrust you can think of as just being an axis that is the best axis that you can draw through your two-jet event, such that when I project the momenta onto that axis, I absorb up as much momenta as possible. And then what you want to state for your thrust is how much of the total momentum have I projected onto that axis. If the total thrust is 1, then that means I managed to project all of the momentum in the event onto that particular axis. And so therefore, there would be no width at all to my jets. They'd be perfectly on top of my axis. And as my thrust moves away from 1, then you can see that I'm going to be measuring the width off of that axis that I have, because that means that there's a little bit of momentum in the event that did not get projected on the axis that's moving transverse to it. And so in this particular event, the thrust value they quote is 0.987. So appropriately normalized to 91 GeV, that's telling you just how much momentum is being projected upon the axis that you could easily draw in your head of sort of the best fit axis where most of the momentum is going to go. So as you can see, this really is a two-jet event. Most of the momentum is flowing along a particular axis in the scattering process. So we learned last week that when we want to construct an effective field theory, that we need to first discuss the degrees of freedom. And so what are the degrees of freedom for soft collinear effective field theory? Luckily for us, it's all in the name, and we can all go home because we know the name. It's soft, which by that I mean they're going to be excitations carrying very little energy relative to whatever the hard interaction scale is. They're collinear. These are excitations which carry a lot of energy but are clustered about a specific direction. And of course, there's going to be hard. And these are excitations that carry a lot of energy, have no preferred direction relative to the collinear, and set in motion the energetic scattering event. And by and large, you should think that the hard degrees of freedom in my problem actually all have to do with the quantum mechanical fluctuations that set the hard scattering event into play. And they're not going to be an observable degree of freedom in my effective theory or in my detector. If I go back to my little opal detector, all of my hard degrees of freedom would be at that little red dot, highly localized in space and time, which is the quantum mechanical fluctuation of the Z boson itself, and then how that quantum mechanical fluctuation of the Z boson decayed into a quark-antiquark pair, and then how those quark-antiquark pairs started interacting with each other. Now, that all happens on a time scale that's roughly 1/91 GeV, which is a very short time scale. And also, there's nothing about that process that we directly observe in the detector. What we actually directly observe in the detector are the soft and collinear degrees of freedom. In other words, all of the highly collimated energetic particles about my preferred directions, and then any stray soft particles that will wind their way off that axis. And so often you'll hear the language in effective field theory that you'll have on-shell and off-shell degrees of freedom. The off-shell degrees of freedom would in this case be the hard modes that have to do with the production of the Z boson and its initial decay, whereas the on-shell degrees of freedom are these soft and collinear particles. Those are the ones that we pretend are the ones that are going to wind up in our detector, are sort of the observable consequences and the ones that we want to have an effective theory for. And what we'll learn in the course of this talk is that we are going to have a partonic description for these soft and collinear degrees of freedom. However, they're not going to be, strictly speaking, quarks and gluons. And we'll see why they can't, strictly speaking, be quarks and gluons in the course of this talk. They need to be appropriately dressed. In other words, they're going to come along with a whole entire structure beyond the single quark and single gluon that you're used to in normal perturbation theory. And indeed, there's going to be lots and lots and lots of potential quarks and gluons that can all be created by these soft and collinear excitations. And that's why I refrained from calling these soft and collinear degrees of freedom, strictly speaking, quarks or gluons. They're a bit more than that, but they're also a bit less than a hadron. Now, in a very broad overview sense, what's going to happen when we write down these degrees of freedom, and we're going to try to construct an effective theory for it, we will find that these degrees of freedom will interact in what would be called a factorized sense. And we'll see an example of this we'll work through an example of this factorization in the course of this talk. The hard modes that I talked about earlier that are off shell will get integrated out, and they will form what would be called matching coefficients to our operators in the effective theory. And if you go back to last week when we talked about jelly, you should think of this as being exactly analogous to the speed of sound in my jelly. What formed the speed of sound in my jelly, of course, is all the microscopic physics of the jelly itself. You know, what exact proteins I put in there, what are the ratio of protein to water, how much starch is in there, what temperature does my jelly sit at. All of that type of stuff goes into the calculation of the speed of sound of my jelly. But in my effective theory for jelly, it just appears as a single number, the speed of sound, that multiplies some operator in my Lagrangian when I wanted to formulate my effective theory for jelly. The same thing is going to happen in SCET. There's going to be all of these highly virtual fluctuations that are at energy scales that are very large. That will be, quote unquote, integrated out or calculated and then put into a matching coefficient, a number that's just going to sit in front of our operators in our effective theory. And that's how we're going to deal with those hard degrees of freedom that I talked about beforehand. The soft and collinear effective degrees of freedom, we are going to think of as being independent sectors of the theory that by and large do not interact with each other and that are only sensitive to the total quantum numbers of the other sectors. One way that people like to schematically say this is that when we construct our effective theory, I'm going to have some Lagrangian for my full theory QCD, and that Lagrangian is going to become the sum of Lagrangians for each one of my different collinear sectors plus one overall soft sector. And this is a very convenient lie. It's not actually true, but for the purposes of this talk, this is a good way of thinking about it. And what I'm really saying here is that basically, after this hard interaction, when I'm looking at the formation of this jet on the right-hand side and the formation of this jet on the left-hand side, I can treat the formation of each one of those jets as essentially being independent in its dynamics of what's going on in the other jet, up to the total quantum numbers of that other jet. And I'll illustrate more what I mean by the other jet only sees the total quantum numbers of the other jet as this talk progresses. All right. Oh, so, all right, I've shown this already. I'm showing it again. Why do I know that these are my degrees of freedom? Well, once again, I could just look at my detector readout, and hopefully you'd be convinced that when I say, I should pay attention to soft and collinear degrees of freedom, just looking at this detector event would convince you of that fact. Clearly, there are collinear degrees of freedom. There are two jets. Lots of particles are clustered around a particular axis, and they carry the bulk of the energy altogether of the event. And there you do see these stray detector readouts at wide angles away from the jets, say this really bendy blue track, or that little green blip that's at the very top. Those would be some very soft particle that was not associated with either jet. And so just by looking at this picture, you could say, okay, it makes sense he wants to talk about soft and collinear degrees of freedom. But you would have also come to the same conclusion that you needed soft and collinear degrees of freedom by just starting doing some perturbation theory in QCD at high energies. So since this is what I did my thesis on, I'm not going to talk about jets produced particularly by a decay of a Z boson. Instead, we'll think about the decay of a Higgs boson, just because I think the construction of gluonic SCET to be a little bit more interesting than the fermionic version of it. One thing that you could sit down and do, and it's a pretty easy calculation, is that you can modify your standard QCD Lagrangian to have a h times f squared operator. In the standard model, this would be generated by integrating out the top quark and matching to an effective theory of the standard model that has your QCD Lagrangian plus your Higgs field coupled to your field strength tensor squared for your gluons. And what this describes is, for instance, how one might take a Higgs boson and decay it to two gluons. And here I've labeled the two gluons to have a particular momentum, Pn and Pn bar. They have particular polarization vectors associated with them. And for convenience, I've also calculated the what I would call hard amputated process. It's basically just the Feynman rule for that vertex in the middle of the slide. And when I contract these polarization tensors into this amputated hard process, I will get to lowest order in perturbation theory the amplitude for how a Higgs boson could decay into two gluons. Now, immediately, you're going to conclude that there's going to be a large energy deposited into those two gluons. The Higgs boson, as we know, sits at about 125 GeV. In the rest frame of this decay process, each one of those gluons is going to have to carry roughly half of that energy. And so they're going to be moving rapidly away from each other with an energy that is on the order of 60, I guess, 2 GeV. And this is going to define for us, therefore, a light cone coordinate system that we'll use throughout this talk to discuss our degrees of freedom. In the rest frame of this decay, the two gluons are moving back to back from one another. So I can take each one of those gluons to define for me a light cone direction. And these light cone directions I'll call n and n bar. And if you want to think about it as a 4-vector, then I list the particular coordinates of the 4-vector for you. The z direction is just going to be defined as whatever is the direction that the gluon is moving in. One gluon is going to be moving in the positive z direction. The other gluon is going to be moving in the negative z direction. And I can take any Lorentz vector that I want and split it up into a coordinate system where I have one part that's parallel to my light cone direction in bar, one part that's parallel to my light cone direction in, and then there's going to be whatever is the transverse fluctuations away from that. So in 4 space-time dimensions, those transverse fluctuations are going to form a 2-vector, which is just the spatial momenta in the plane transverse to the axis defined by the back-to-back gluon system. And importantly, the sort of relations that you need to know about these two light cone vectors is that they're going to square to 0, and if I dot them together, I'll get 2. And once you understand light cone coordinates, you've probably understood the most difficult part of SCET. So if you've never dealt with light cone coordinates before, I suggest spend a lot of time decomposing vectors into light cone coordinates and understanding how that works. Once we have our light cone coordinates in place, I'm going to skip ahead a little bit and talk about the power counting, because in the construction of SCET, unlike the construction of my jelly, it's a lot harder to just separate degrees of freedom, symmetries, and power counting from one another. The 3 sort of interact non-linearly with each other. So you have to forgive me if I jump around a little bit in my talk between each one. hopefully I can sketch for you a clear picture of what's going on. So now that I have these light cone coordinates, I can give you a much more rigorous definition of what I mean by collinear, and technically I'll call it ultra-soft momenta. So we had our hard scale mh that's roughly given by the mass of the Higgs boson. And I'm going to introduce a power counting parameter, lambda, which is a dimensionless number that I'm going to demand to be a lot less than 1. And I will call a parton collinear to the direction in if its momentum satisfies a particular set of scaling relations when I break it down into these light cone coordinates. In particular, the n bar dot p component is going to be of order m. The n dot p component is going to be lambda squared suppressed relative to it, and the transverse component is going to be suppressed by order lambda relative to the largest component. And we're going to call a parton ultra-soft if its momentum satisfies a scaling where each one of the components is basically isotropic in the scaling with respect to lambda. In other words, there's no preferred direction to my soft. All of the momentum components are scaled down. And you can also define anti-collinear, where all you do is going to swap the roles of n and n bar. If I talked about an anti-collinear or an n-bar collinear particle, then you should just think that this lambda squared should move from the n dot p to the n bar dot p. And finally, given an operator in our field theory, we will label it as being collinear or soft when its derivative will be treated with the same scaling. And this should make a lot of sense to you. The derivative is telling you what is the momentum being generated by that particular operator that you've written down. And so if I think about the derivative acting on my operator as being itself just a type of momentum, then I can call that operator soft or collinear if I treat that derivative as having a scaling like that of collinear power counting or an ultra-soft power counting. And I apologize for this a greater than 1. That's a previous version of the slide that made the slide more complicated that I later deleted, but I forgot to delete the a greater than 1. So I promised you that by the analysis of just perturbation theory, we would be able to rapidly see why we want to pay attention to these soft and collinear degrees of freedom. And earlier, we had the process, let me go back, of this Higgs decay to 2 gluons. And we can think about a related process where we brim off an extra gluon and ask what happens. In particular, what's going to be interesting when I add this extra gluon into the diagram and I calculate what this diagram is, I will find that particular limits of this diagram are enhanced. In particular, if I were to go and declare that this gluon is ultra-soft, I could expand this full Feynman diagram, plus all the other ones I didn't write down. You need to write down the complete set and sum them. I can expand them in that soft limit as given on my previous pages, and I will find that my 3 gluon decay amplitude is going to look basically like the product of my 2 gluon decay amplitude times these soft iconal factors. And what's important about these soft iconal factors is that they support a singularity that is going as 1 over lambda squared as lambda goes to 0. And so this is an enhanced limit of QCD perturbation theory, this particular soft limit, that's doing 2 interesting things for me. One, as I take the soft limit of this soft gluon that I've brimmed off, the hard configuration that I wrote down on an earlier page is coming back to me as this, as you can see in this product form. times this soft iconal factor. And you can do a similar exercise, which I'm not going to show in this slide, where instead of taking that gluon to be soft, if you were to take it to be collinear with the same power counting in the Feynman diagram, as I wrote on the other page, you're going to find that the collinear limit itself is also enhanced as lambda goes to 0. In other words, there's going to be a particular propagator in that those Feynman diagrams that is becoming singular as I'm entering this collinear limit. And because you have this enhancement in the Feynman diagrams, you would say, these limits must be important. There must be something important going on in these soft and collinear limits. And that would motivate you, just the analysis of fixed order perturbation theory, even if no one ever handed you a detector photograph like I did, that you should pay attention to the soft and collinear limits of a scattering process in QCD. So why do I have soft and collinear degrees of freedom in my effective theory? The two reasons are basically this. The soft collinear limits are singular. I've introduced that power counting. I expand my diagram of a higher order process in that power counting, and I'll find these singularities. But there's also another reason, and that is partons cost nothing. You have to remember we're operating at high energies in QCD, so all of my partons can be treated as if they're effectively massless. If I have some emission and I want to address it with another parton, it costs me nothing, relatively speaking, in terms of energies, because there's no intrinsic mass to the gluon or the quark. Therefore, you can come to the conclusion that if I started with a process which was just Higgs goes to 2 gluons, as that process evolves in time, then it should be dressed with arbitrarily more soft and collinear partons. And that's coming, like I said, out of these two reasons. One, there is enhancement to the phase space of the production of these soft and collinear partons. In other words, it's a singular process in QCD. And next, it costs nothing. I can always add another parton with relatively little energy cost. And so when we're going to talk about the Higgs decay to gluons, we really shouldn't think about the Higgs decay to 2 gluons, but rather we should think about the Higgs decay to 2 jets, because I know as I perform my perturbation series, I will have to dress those 2 initial partons with more and more emissions, both real emissions, but also virtual loops that I'm not showing here. And so if I wanted to go and, say, calculate a cross-section to hand to my experimentalist friend, it's not going to suffice for me to just calculate for them that Born level process that I showed earlier, but rather what they're going to be interested in is how Higgs is going to decay into any possible 2-jet configuration. And in particular, what's interesting about the 2 limits of soft and collinear is that they preserve, more or less, this Born configuration, both kinematically and in its amplitude. Kinematically, this should be obvious. If I take 2 partons and I split them collinear, then basically the same amount of energy is moving in the same direction. And if I take a collinear parton and I let it brim off something soft, it's not going to move much. There's not going to be a lot of recoil in the momentum. And so I can take my 2-jet configuration and I can start adding softer collinear radiation to it. And yes, I'll smear out that Born configuration as I sort of schematically shown in this picture, but I'm not going to radically change it. And this should be a point that goes back to what we were discussing with our jelly. When I wanted to talk about a power counting, I always had in mind that there was some sort of primal state of affairs, and my power counting was telling me how I'm going to do fluctuations or displacements away from that primal state of affairs. In the high energy scattering process, the primal state of affairs is whatever is the Born configuration that I'm really interested in. Here, it's that two-jet configuration. A Higgs goes to two gluons. That's my primal state of affairs. And what the power counting is telling me is how I can dress, basically, that Born level configuration with soft and collinear emissions and perhaps smear it out. In other words, I'll have some fluctuations about it, but I'll essentially preserve that primal state of affairs, that Born configuration. And so there's lots of wonderful things that are happening for me simultaneously. One, QCD likes the soft and collinear limits. They're singular in perturbation theory. When I take those limits, I will recover back, in some sense, my Born configuration, as was seen in the soft expansion that I did earlier, where I had some soft factor times my Born amplitude calculation. And so this is definitely why we want to think about the soft and collinear degrees of freedom and have the particular power counting that we're assigning to it. So I've jumped a bit, right? We've talked about the degrees of freedom. We've talked about the power counting, and I jumped over the issue of symmetries. Now we'll have to deal with the issue of symmetries, because hopefully I've convinced you in this entire discussion that when I want to talk about Higgs decay to two gluons, I don't want to talk about just that Higgs decays to two gluons. I want to talk about a Higgs decay to two jets. And so I would like to write down an operator in my effective theory that allows me to create any two-jet configuration for a Higgs decay. But if I'm going to write down an operator in my effective theory that creates any two-jet configuration, I'm going to have to think about the symmetries of the theory, because that's going to inform me how I'm going to go and actually construct the operators necessary to do this in my effective theory.
Hi, sorry, I have a question.
Sure.
So when you talk about the fact that we should really be interested in soft and collinear modes of our particles, you say that it's sort of the result that these limits are important in our cross-section. How can we show that these are the only limits? How do we know that there's not secretly some extra?
Good. So this is always a worry with an effective theory construction. You can worry, right, that I'm going to write down all these low energy modes. In particular, I'm going to write down these soft modes. I'm going to write down these collinear modes. And hopefully that's enough degrees of freedom in my problem in order to reconstruct my scattering process in the limits I'm interested in. And you might say, but what if, basically what you've asked is, but what if there's another mode and you're not that smart, Duff, and you forgot about it? This can definitely happen, has happened many times in the literature. And what you hope is when I perform what's called a matching calculation, that my soft and collinear limits is sufficient. In other words, it should always be the case that when I calculate in my scattering process in the quote-unquote full theory, and then I subtract from it my effective theory answer, the result should be something that's power suppressed. In other words, it's going to zero as lambda goes to zero. Or technically for us, it would actually go to a constant as lambda goes to zero, because my first order and my power series expansion is singular. If I find that this is not the case, in other words, I have all my modes, I've constructed my effective theory, I've calculated my process in my effective theory, and I subtract it from my full theory, and then I expand in the limit, and I find something that's still singular, that would be a check that I've performed that would tell me I am missing a mode. Sometimes nature is devious. You can write down all the that you think you need by just analyzing, say, a tree-level process or analyzing a one-loop process. And then you go and you calculate to 2 loops, and you find that you need another mode.
Okay, yeah, thank you.
And that you just didn't see it until you did the 2-loop calculation. This is what sort of informs the art of effective theory. People have tried to make this into a more rigorous algorithmic type of calculation. And in particular, there's something that's very much related to effective theories called the method of regions that people use for calculating loop amplitudes. And in the method of regions, you kind of do a very similar analysis that you do in an effective theory. You think about various different regions of a loop calculation being in some collinear region or some soft region. And these people that do these loop calculations have tried to write automatic programs that will spit out for you, by just analyzing the Feynman diagram in an algorithmic way, all the regions that you needed in order to do this type of expansion and reconstruct the loop integral in that limit. These algorithms have no definitive proof that they work. There's still an art to that, even in the method of regions. So up to now, no one has given sort of a complete proof. In all instances, this is everything that suffices in order to reconstruct my QCD in these high energy scattering limits. In particular cases, we can give a proof. For particular scattering processes, we can give a proof. But we can't give a proof for an arbitrary scattering process. As far as I know, no one's constructed such a proof, or maybe I should say an algorithm that would spit out for you a proof for any given particular scattering process. Does that answer your question? I know that took me pretty far afield.
No, that answers perfectly. Thank you.
But I mean, you can even think about a matching calculation early, in this soft limit. Right. Here, I took my full theory diagram and I expanded it in a soft limit, and this is the answer I got. There should be an exactly analogous calculation that I would perform in my effective theory, and the difference between these two should be 0 up to this ... Right? And that would be an example of a matching calculation that you would want to go and perform to check that you do have all your modes. And so if I was missing something about my soft mode, then I would find that when I did this sort of matching between the two processes, I would get something that's still singular in that lambda goes to 0 limit. So now I'm going to get into the symmetries of SCET and how we're going to go about in constructing our operators. Now, the basic intuition of the construction of our operators is that we would like to take, say, some full theory quantum field, say my gauge field A mu, where I'm listing both its Lorentz index and its color index. And intuitively, what I would like to do to my sort of full theory gluon field is split it up into, say, a in collinear gluon field, an in bar collinear gluon field, and an ultra soft gluon field. And that goes back to the earlier picture where I said I'm going to take my full QCD Lagrangian and I'm going to expand it into these sum of different collinear sectors plus my soft sector. And I would like to demand that these fields, my gluon fields, are quantum fields that interpolate in collinear, in bar collinear, and ultrasoft particles only. And remember, I'm labeling a field as being in collinear, in bar collinear, and ultrasoft. When the covariant derivative acts on that field, it would power count in the same way as an in collinear momenta, in bar collinear momenta, or an ultrasoft momenta. However, you should stop me right now and say, I can't construct an effective field theory using my gauge and quark fields alone, because these objects are not gauge invariant. And we wanted to construct a effective theory, as we learned in the case of the fluids, that respects the symmetries of the problem. And hopefully, when we talked about the case of the jelly, I was able to convince you that it's very important to pay attention to the particular symmetries that you write down for your theory. Because if you change those symmetries slightly, you might get a very different theory. You might go from a jelly to a liquid. Now, normally, in gauge theory, the way we deal with gauge variant operators is that we basically square them up appropriately. So for instance, my field strength tensor is going to transform in the adjoint of my gauge group. And if I square it up with another gauge field tensor, I'm going to find something that's gauge invariant. And I might do something also with my quark field operators. If I just square them up with another quark field operator and I contract together those sort of color indices, then my gauge transformations will just cancel between my different operators that I'm writing down. And so by and large, when we first learn about gauge theory, we're just told, okay, you have these operators, they transform according to my gauge group, and if I just square things up nicely, I will get something that's gauge invariant. And so you'd be tempted when you're going to write down SCET that in order to get gauge invariant operators to describe my effective theory, I should just do some similar procedure of squaring up my operators in order to get something gauge invariant. Unfortunately, this option is not sufficient in SCET. This is not going to be an option that we can make use of in the construction of our effective theory. And the reason why we cannot square up operators is essentially because of problems with locality in a high-energy scattering process. In my construction of QCD, where I would just square up those operators, note that I have to square them up locally. In order to cancel the gauge transformation, these two operators need to be at the same space-time point. And that's because the gauge transformations themselves are local. They're happening at every single space-time point, and they can be effectively independent at every single space-time point. And so if I'm going to square up operators, I have to demand that they are sitting at the same space-time point, and that would cancel the gauge transformation at that particular space-time point. But we can immediately see that as soon as I analyze my lowest order process, my Born configuration in QCD, any operator that I write down at lowest order in perturbation theory has to create a single n-collinear gluon or a single n-bar collinear gluon, because that's what's happening in my lowest order QCD process when I calculate the scattering amplitude. And any operator that I went to write down that was gauge invariant by this squaring up process can't create a single gluon, can't create a single quark, right? Because my squaring up gives me bilinears, I will always create them in pairs. And that makes sense. Those operators are gauge invariant, they're color neutral, and therefore they can only create color neutral systems. So they can't create a single gluon, they have to create two gluons that color neutralize with each other. They can't create a single quark, they have to create an anti-quark with it in order to color neutralize it. But I want to create, at least at lowest order in perturbation theory, a single quark or a single gluon that's going to represent sort of the progenitor of my jet. And was there a question?
No.
And each one of these sectors is going to enjoy, hopefully, as I claimed earlier, independent dynamics, basically due to causality. These gluons are rapidly moving away from each other, and so the amount of time that they could be in causal contact with each other is going to be very, very short. And once they're not in causal contact with each other, they better have just independent dynamics. And that's just due to the high energy scattering process itself, the fact that I've dumped a bunch of energy into some small localized region, that energy is going to fly away and try to escape. And once it leaves that small localized region, the different particles will no longer be able to interact with each other. The solution that's available to us is to solve our problem of gauge invariance non-locally, and that's to use something called a Wilson line. And now a Wilson line is just where I'm going to take my gauge field, and I'm going to exponentiate it into this path-ordered exponential. And here I'm going to be talking about a collinear Wilson line. So unfortunately, in collinear Wilson lines, and this is just the notation that was adopted early on in SCET, is that an incollinear Wilson line is a gauge field that is exponentiated along a path which is in the n-bar direction. And what you should think of this Wilson line as describing for you as a generic charge, where I've written my charge down as this T matrix, being transported along from point X to a light cone ray emanating away from point X off to infinity. And as that is transported along, of course, it can brim gluons, and that's the coupling of the charge to the gluons in the exponential. And the path ordering is just because I have to take into consideration that since I have a non-abelian gauge theory, I have to multiply, as I expand that exponential, all of those charge matrices in the appropriate order. What's nice about a Wilson line is that my covariant derivative annihilates my Wilson line at a space-time point. Another way of thinking about that is that the Wilson line will render my covariant derivative as being inert. In other words, I can always take my covariant derivative in the n-bar direction and use my Wilson lines to pull out the gauge field, and I'll be left with a normal derivative, a derivative with no gauge transformation properties. The way to think about that is that what my Wilson line is going to do for me is that it will transport my gauge transformation that's happening at point X to infinity. And once my gauge transformation is at infinity, then I can pretend that it's not a problem for me anymore. And so I can solve this problem of that it seems like in order to get a gauge invariant operator, I needed to square things up. But when I want to describe my scattering process, I still want to talk about single quarks and single gluons. I'll be able to solve this problem by the addition of a Wilson line. In other words, by using this trick of rendering covariant derivatives inert, I'll be able to move my gauge transformations away from my space-time point at X and off to infinity. And so I'll just write down for you the solution. You introduce this B gauge field where I take my n covariant derivative in the transverse direction, and I act on my Wilson lines with it. Now note, it's the n-bar direction that annihilates the Wilson line, or that sort of renders that derivative inert. So hold on, I have it. Sorry, my phone was ringing. I just lost my thought. The next derivative I have available to me in the power counting, once I've rendered my n-bar derivative inert, is of course just the d-perp derivative. That was the one that was down just by lambda. There's, of course, the other derivative that's down by lambda squared, but we don't need to worry about it at this point because that's just power suppressed relative to this derivative. This defines for me a gauge invariant field operator that can create a single gluon. And this is the object that I needed in order to be able to describe my lowest order scattering process in QCD. The perp just denotes that projection onto the transverse directions for the mu index. And if you really wanted to see that I can think about this as being a creation and annihilation operator of a single gluon, if I were to go to some sort of light cone gauge, then I would trivialize these Wilson lines, and you would find that my B perp operator is just my gluon field operator in the light cone gauge. In other words, it really can just create in the light cone gauge a single quark or a single gluon. Now, I don't need to rely upon a particular gauge choice. I've constructed a gauge invariant object here. And so I can calculate in any gauge I want to, as long as I take into consideration that I'll have this Wilson line. Now, this solution to my problem seemed incredibly formal the way I just threw it at you. I have gauge transformations. I don't like gauge transformations. I need something that's gauge invariant. So I'm going to throw in this Wilson line, and it's going to make it gauge invariant. That seems like an incredibly formal solution to this problem. However, these Wilson lines are not just a formal trick, but actually capture an important physical intuition about what's going on in my scattering process. My jet is created by some local operator, my covariant derivative at some space-time point, embedded in a larger physical process. In other words, I have a jet, but there has to be some other jet that it's recoiling against. This larger physical process has to appear as a non-local object to the jet that I'm concerned about, right? I've dumped a whole bunch of energy down into some small space-time point, but it's not going to stay localized as time evolves. Instead, it's going to spread out and go off to infinity. And so in the course of the evolution of my jet, it is going to be sensitive, in some sense, to this larger physical process that is the scattering event. And that larger physical process that's the scattering event is going to take place over my entire space-time region available to me. In other words, it's going to be some type of non-local object. From the perspective of my jet, all the other scattering particles are rapidly moving away from my jet. And this is why I chose my n-bar path for my Wilson line. In other words, that's the path that's in the recoiling direction from the direction that my jet is going in, which is the n direction. And finally, all of those other particles that are traveling in this n-bar direction from the perspective of my jet can radiate gluons, n-collinear gluons, into my jet. And in fact, they'll radiate in precisely the way, precisely with the anti-charge that's needed to color neutralize my jet. But what's important is that I can pretend that all of those other particles are doing it with no internal structure. In other words, it appears as a structureless charge moving along this n-bar direction, radiating n-collinear gluons into my jet, but there's nothing else about that rest of the event that I need to know, nothing about its actual internal structure. So my jet will see all the other jets as being just a structureless charge moving fast away from it, a structureless charge moving fast away from it in precisely the right representations to color neutralize the jet I have. And I won't be able to resolve any of the internal structure of those other jets. So this Wilson line, far from being a formal trick, is actually capturing an important physical intuition for me about the scattering process. The Wilson line is precisely the anti-charge that my jet needs, with no internal structure, needed to color neutralize my jet in the larger scattering process that it's embedded in. The reason why I say that all the other particles in the scattering process have no internal structure relative to the perspective of the jet that I'm evolving is basically back to that causality argument that I alluded to earlier. Any internal structure that's happening in my n-bar jet, and so you can think about that internal structure as being its own sort of Bremsstrahlung that it's enjoying, maybe some loop process that it's undergoing. All of that internal structure is happening at time scales that are much longer than the time scale where my jets were actually in causal contact with each other, which was just the hard interaction. That time scale of the hard interaction is like 1 over the mass of the Higgs boson. And all of those loops have to do with time scales that are at energy, that are at time scales much longer than that. And that's what's allowing me to replace this complicated n-bar jet that's recooling my n jet with just my Wilson line, as I represent as a black line, that's radiating these charges in sort of with no internal structure. So that's how I'm going to deal with my collinear physics. I'm going to use these Wilson lines, and these Wilson lines are capturing an important physical intuition for me, which is that my jet is embedded in this larger physical process, and that there has to be something non-local happening in that larger physical process, but it's happening in a universal way. It's non-local, but universal. And that universality is coming out for you basically from the symmetries of the problem. I need to color neutralize my entire system. And so there's only one way at leading power for me to do that color neutralization, which is that Wilson line. So how do we deal with the soft physics then? Well, once again, we wanted to take our full QCD covariant derivative and split it into a collinear covariant derivative and an ultrasoft covariant derivative. And you can think about what would happen when we try to construct a Lagrangian for my full theory, and I try to substitute in this d mu as being some collinear covariant derivative plus some ultrasoft covariant derivative. If I were to substitute that in, and you have to remember, I'm going to get a whole bunch of terms. I'm going to throw away some terms based on just the power counting of these two derivatives and the different components. So I'll have to break these guys up into different light cone components. And then I'll stick them in there and I'll do some power counting. I'll throw away a whole bunch of terms. And I'll find that I'll always throw away my soft covariant derivative, my ultrasoft covariant derivative, whenever it's being added to either a transverse component of my collinear or the m-bar direction of my collinear. And that just goes back to my power counting. Oop, wrong way. Where did I map? Here. If I look at the different components for ultrasoft versus collinear, I find that if I were to add an ultrasoft momentum in the n-bar direction to my collinear, then I'm going to get a suppression that's of order lambda squared. In other words, n-bar dot p is of order m, but n-bar dot p for my ultrasoft is order lambda squared. And so when I add these two components together, I would always drop my ultrasoft. Same is true for the transverse. My transverse collinear is going to be order lambda, but my transverse ultrasoft is going to be order lambda squared. It is only going to be in the n direction, or not the n direction, the n dot p component, where the two have the same scaling, this order lambda squared scaling. And so that will be the only component in my Lagrangian of my ultrasoft that I can keep according to the power counting. And so when I write down my full covariant derivative, as being this collinear covariant derivative plus an ultrasoft covariant derivative. The only component of my ultrasoft covariant derivative that I'll have to worry about is the n dot component of that ultrasoft covariant derivative. But based on our discussion of the Wilson lines that I discussed earlier, this should immediately tell you that there's a trick I can play in order to get rid of this ultrasoft covariant derivative in my collinear sector. Because only one component of that ultrasoft covariant derivative is appearing, all I need to recall is that Wilson lines could always render a covariant derivative inert. You should forget about the n bar dot mu divided by half on the left-hand side. The n dot ultrasoft, which is a covariant derivative containing my ultrasoft gauge field, that ultrasoft gauge field can be removed from that derivative by just using that Wilson line trick that I used in the construction of my collinear gauge operators, gauge invariant operators. All I have to remember now, though, is that I have to point my Wilson line in a different direction. I can't point it in the n-bar direction, which is what I did for the collinears. Instead, I need to point it in the n direction. And that's just dictated to me by the fact that I have this n dot ultrasoft. So we'll be able to get rid of any ultrasoft content of my collinear Lagrangian by just doing a field redefinition, where I just go and redefine all of my collinear field operators with a soft Wilson line. And that will basically render all ultrasoft derivatives inert and remove all ultrasoft physics from my Lagrangian. So, how do we combine all of these ingredients together to construct my two-jet operator? So this is just to recall the Boyne level process that I want to think about. I have some Higgs boson going to two gluons. And I'm defining my amputated hard process. And so this is just to remind you something that I wrote up earlier. Well, I know I need to be able to, at lowest order in perturbation theory, create a single collinear gluon and a single anti-collinear gluon, one in the n direction, one in the n bar direction. I have to be able to reconstruct that hard vertex, in other words, that amputated hard amplitude that I wrote down on the previous problem. And so then my claim is, if I want to be able to construct all possible two-jet processes in my effective theory, this operator that I'm writing down here is sufficient to do so. We've gone through the argument that this Bn operator is gauge invariant, this Bn bar operator, which is just the exact same construction, but now in the other collinear direction. And I'm going to construct this before I've removed my ultrasofts, before I've done my field redefinition. And there's going to be a convolution between these collinear operators and my hard scattering amplitude in these energetic light cone directions. In other words, this delta function is just saying, what is the total energy of one of my collinear sectors? It just asks that question, and then it dumps that total energy into my hard process. Once I do my field redefinition to remove my ultrasoft content from my Lagrangian, I will find that my two-jet operator that I write down to describe these two-jet scattering processes is now going to be dressed by soft Wilson lines. So I'm going to remove the soft content out of my Lagrangian, and it's going to get stuck into my two-jet operator, which is where it belongs. And then, at the end of the day, this is the operator I'll have. I'll do my field redefinition, and I'm going to get this product of Wilson lines, and I can just move them on through, and I'll have two Wilson lines, ultra-soft Wilson lines, that represent how soft radiation can brim off of my hard scattering process. That soft radiation is only sensitive to the total color charge of each one of my collinear directions. And it moves parallel to each one of my collinear directions. And then I'll have some my collinear operators, which describe for me how I can create a spray of collinear particles coming out of it. I'll have a convolution between my energy of each one of my jets into my hard scattering process. And that's just necessary in order to balance out the kinematics. So what do we really mean by this two-jet operator? What is it really doing for us? Well, we should go and sit down and do a calculation with it in order to get back some intuition about what this two-jet operator is doing. Let's define psi to be a partonic state in full QCD that's consistent with our power counting. And I'm going to pretend that I can split psi up into a tensor product between some collinear sector, some anti-collinear sector, and some ultrasoft sector. And you should just think of this psi bar, psi ultrasoft as just being lists of momenta and polarizations that respect my power counting. In other words, if some momentum P is a member of psi n, then its momenta respects my collinear power counting. If it's a member of psi n bar, then its momenta respects my anti-collinear power counting. And if it's a member of ultrasoft, it respects my ultrasoft power counting. So this is precisely the type of state that would be annihilated by my two-jet operator. And so the matching calculation that I referred to earlier is just going to be the statement that the scattering process that I calculated in full QCD on the left-hand side better equal the scattering process that I calculate in my effective theory up to power corrections in those singular limits. Moreover, once I calculate with this state, you can kind of see immediately what's going to happen to my two-jet operator. That convolution I wrote down earlier is just going to go away. My hard scattering process is only going to be sensitive to the total energy in one collinear sector and the total energy in the other collinear sector. And this is the same hard amputated hard scattering amplitude that I wrote down earlier. I'm going to have some matrix element of my collinear field, some matrix element of my anti-collinear field, and then some soft matrix element. And this is just entering as a product with each other. Quite literally a product. They are aware of each other's total quantum numbers, as I alluded to earlier. The hard scattering process knows the fact that my collinear sector is being generated by some spin 1 gauge field. In other words, there's a Lorentz indice contracted between the two. And of course, the total color charges are going to be known to sort of everyone. There's the total color charges that are coming out of my hard scattering process that then go into my collinears. But first, they're going to get dressed by all my soft radiation. That's accomplished to me by my soft Wilson lines. The important point is that you should not think that these color indices have any gauge transformation properties. These are global color charges that we're talking about. They've all been transported nicely off to infinity by my Wilson lines. And so everything as it's constructed is nice and gauge invariant because I can always pretend I have no problems at infinity, at least in perturbation theory. And in particular, if I were to write down a very nice state that respects my collinear power, that respects my power counting, In other words, I take my soft radiation to be in the vacuum, and I just use my Born level states, and I calculate what's going to happen in these matrix elements up above. I will find that my two-jet operator is actually precisely constructing for me my Born configuration. In other words, each one of these collinear operators is just going to become my polarization tensor. My vacuum expectation value of my Wilson lines is just going to be a bunch of Kronecker deltas in my color indices. Everything will contract together nicely, and I'll just recover my Born level process with this trivial calculation. But I could go on and I could calculate something more complicated. I could, if I wanted to, make my ultra-soft state to be non-trivial, stick in some non-trivial soft bremsstrahlung, do the calculation, and if you were to go through and expand out your Wilson lines and calculate everything to first order in perturbation theory, you would in fact recover from my two-jet operator precisely this expression here. And you can almost see the structure of how that's going to happen in my two-jet operator that I wrote down. My two-jet operator has already this factorized form of the tree-level Born process times some soft matrix element. The only complicating factor is just what happens to the color indices, but that is actually just handled for you automatically in the definitions of these Wilson lines. So it's useful to go back and look at exactly what we did back in the context of our discussion of jellies the previous week. While the addition of gauge theory made it more exotic, and basically because I'd said I have to deal with a gauge theory, it forced me to deal with these non-local objects like Wilson lines and so on and so forth. The construction of my power counting is a bit more complicated because in my jelly, I could presume that everything was sort of isotropic in my jelly. And so when I power counted my derivatives in my jelly, I just said my derivative acting on my field element is always suppressed. That doesn't quite work in SCET. In some directions, it's suppressed. In other directions, it's not suppressed for, say, the collinears. Up to those caveats about having to think about directions, I went through the exact same procedures as I did with our jelly. I asked the question, what are the degrees of freedom? And I did some thinking in order to figure out what that is. I had to deal with the symmetries. In other words, how are those degrees of freedom are constrained? In the jelly, it was those global rotations that constrained my, my jelly, the fact that my jelly had no internal structure. In gauge theory, it's going to be this gauge invariance that's the biggest constraining factor. I had to use my power counting. In other words, I had to ask, what is the primal state of affairs and what are the fluctuations about it? And how big are those fluctuations? Didn't really talk about what is the principle of least action or the path integral, but I've implicitly alluded to it throughout this entirety of the talk whenever I wrote down a Feynman diagram in order to do a calculation. Perhaps the most difficult part of doing it for SCET relative to the jelly is that in the jelly, I was able to very nice and neatly go through degrees of freedom, then symmetries, then power counting in a nice, just straight line. In SCET, when I wanted to go construct it, I inevitably had to jump back and forth between each one of these. What are the degrees of freedom? What are the symmetries? What are the power counting? Because in SCET, the way that I dealt with my symmetries was actually informed by my particular power counting that I wanted to impose. In other words, it was not for an arbitrary reason that my Wilson line was in the in-bar direction, which also happened to be the most relevant derivative according to my power counting of my collinear direction. In other words, those two facts are intertwined with each other. And this shouldn't surprise you. I'm dealing with a gauge theory, and in a gauge theory, I don't have derivatives, I have covariant derivatives. And so momenta, and the way we like to think about momenta, is inevitably going to be intertwined with the symmetries of my theory when I'm talking about a gauge theory. And so while in a jelly, I could sort of keep these two concepts separate, I could think about the symmetries and the power counting away from each other. In a gauge theory, it forced me to intertwine these two concepts as I went through the construction. All the same ingredients were there. I pursued all the same tactics in the two instances. One was just more complicated than the other, basically because of the underlying gauge symmetry. Now, I made an argument about why we did this. And that argument about why we did this is because I said there was this enhanced phase space in these soft and collinear regions. And addition of partons cost me nothing. And so I should never expect to have a Higgs decay to two gluons. I should always expect a Higgs to decay to two jets. And therefore, I wanted an operator that would be able to describe for me any two-jet situation. What I won't really have time to explain is now what I really want to do with that operator, which is the renormalization and regularization of my effective theory. In other words, I had this argument that I had all of these singularities, and I could dress my scattering amplitude with sort of arbitrary emissions. I would like to have some sort of procedure that would allow me to resum in a nice orderly way all of those dressings. And what will do this for me is the regularization and renormalization of my effective theory. It will give me a set of renormalization group equations that will allow me to resum these singularities in the all-order insertions of the partons that we argued to exist. And when I apply this renormalization group to my effective theory, I will stabilize and rescue my perturbation theory and be able to hand to an experimentalist a cross-section with a good description in perturbation theory. Unfortunately, I will not have enough time to explain how to do all of these things. But ultimately, from a calculational point of view, this is why ultimately I would want to construct this effective theory, is in order to rescue perturbation theory in these singular limits to describe cross-sections in a controlled way and compare with experiment. I have no idea how I'm doing on time, but I think I'm going to end there. And if there's any questions, I'm happy to try to answer them.
Okay, that was fantastic. Thank you very much for this very, very nice introduction to SCET. Interesting. I always pronounce it as SCET, but you were very careful to enunciate each letter in the acronym.
Has to do with who teaches you SCET.
Mhm.
In Europe, they always say SCET. In America, at least if you talk to Ian Stewart, one of the inventors of SCET, he always said the letters out. I don't know why he always said the letters out, but he always did. So like, so if you come from like a more American school of learning SCET, you oftentimes will say SCET. People in Europe always say SCET. SCET is a perfectly appropriate pronunciation. So
it's rare for the Europeans to be more efficient.
I know.
But okay, so questions from the floor. Yeah, please.
Yeah. So when I think you called it, you made the derivative inert with the Wilson lines. You made a covariant derivative, sort of just a regular derivative. Did you?
Yeah.
Does that change the power scaling? It looks like you've gone from something with a soft field into something that doesn't have a soft field anymore.
It doesn't actually change the scaling. So the way that you should think about it is that the actual derivative, the partial, has a scaling. And the soft field has the exact same scaling as that derivative. This is okay from the perspective of my collinear. In other words, the actual derivative, calculus derivative, not covariant derivative, for my collinear field, that has the same power counting as my ultra soft, right? So once I render this ultra soft derivative inert, then I'll have a normal derivative, but that's fine to live in my collinear sector. It has that scale anyways, according to my power counting. What I really want to do is get those ultra softs out of my collinear Lagrangian. That's really what I want to do. And I really alighted over this fact. You can look at the early papers in SCET. They'll discuss this in much more detail. Precisely how you do this field redefinition does actually remove all ultrasofts out of your Lagrangian, and then they get stuck into things like these two-jet operators.
Yeah.
Which is where physically they need to be. So hopefully that kind of answers your question, I hope.
Yeah.
Super. Other questions from audience? I don't see anything online. Okay, awesome. Well, Duff, we've taken up more than the time that you agreed to. So thank you very much for donating even more time to us. Yeah, really appreciate it.
So,
Oh, wait, sorry.
I have one more bit. So like going back to the picture of this two-jet event. In the end, like what sort of quantities we expect to calculate this soft Collinear effective theory?
Yeah, so the actual calculation that I would do is, for instance, I would like to calculate how much energy is actually going to be displaced off of the major axis of this event, for instance. So they would call this either the broadening of the jet. And so in the effective theory, that would be what you would go calculate. In other words, I would calculate the cross-section for my jet to broaden by so much. And you can just think of that broadening as being literally how much transverse energy is moving away from that major axis of this event. And that would be something you would calculate, and then you would give the experimentalists a cross-section for that. They would measure a bunch of events. They would bend those events by the broadening, and you would see if your calculation matched their bending, right?
Okay, so what do you need to supplement the calculations to say something even more than that? Like to like what species of hadrons are going to be hitting detecting?
Yeah, so you don't actually need to calculate the broadening of the event to talk about the specific hadrons and what they're doing.
Oh, okay.
And this goes to a fact called infrared and collinear safety. This is something I didn't have time to talk about at all in my talk. But basically, you can argue that as long as your broadening is much bigger than lambda QCD, it could still be much smaller than, say, the mass of the Z boson. It just needs to be much bigger than lambda QCD. So for instance, I could have a broadening where, say, 10 GeV worth of energy is being transported transverse away from my axis. 10 GeV is still much larger than lambda QCD, but it's still much smaller than 91 GeV. So you can be in a range where I don't have to worry about the specific hadronization process because of this concept of infrared and collinear safety. Below my broadening scale, infrared physics will just cancel. This cancellation of infrared physics below some scale is oftentimes another thing that you want to use effective theories for. You want to use the effective theory to show that the infrared physics is going to cancel below some energy scale in your problem, and therefore you're not sensitive to what that infrared physics is. In other words, you're not sensitive to what the partons are doing at any energy scale below that.
Okay. Good.
Cool. All right, well, let's thank our speaker again. Yeah, thank you so much, Duff. I'm a few, you know, when one goes on a run or goes to the gym in the morning, then everything else for the rest of the day is gravy. So in that sense, I hope you feel the same way today.
All right.
Cheers.
Bye.
So